Breaking news. At 2:18 a.m. UTC this morning, a routine update to the World Magnetic Model triggered an automated alert inside multiple geomagnetic monitoring centers across the globe. What began as a quiet recalibration instantly escalated into a red-level anomaly. Data streams from satellites, polar observatories, and deep ocean magnetometers no longer agreed. The numbers were drifting rapidly. Today, the impossible just happened. Earth's magnetic pole, something we believed we understood within predictable limits, has accelerated beyond every forecast. Not by a small margin, by orders that force scientists to stop, recalibrate, and ask a dangerous question. What changed? This changes everything we thought we knew about the stability of our planet. And if you want more real-time cosmic and planetary updates like this, make sure you hit like, subscribe, and stay with us, because this story is unfolding right now. For decades, the movement of Earth's magnetic North Pole has been carefully tracked by an international network of instruments operated by NASA, the European Space Agency, the British Geological Survey, and research institutions spanning 6 continents. Normally, the pole drifts slowly, on the order of a few kilometers per year, guided by the turbulent but statistically stable flow of molten iron deep within Earth's outer core. But what we detected over the last 72 hours is not slow drift. It is acceleration. The confirmation came almost simultaneously from 3 independent systems. NASA's Swarm satellite constellation, orbiting at altitudes between 450 and 530 kilometers, detected a sudden change in the vector strength of Earth's magnetic field over the Canadian Arctic. At nearly the same time, ground-based flux gate magnetometers at Resolute Bay in Nunavut and Ny-Ålesund in Svalbard reported phase shifts in magnetic declination that exceeded model predictions by more than 400%. Within minutes, alerts propagated to research hubs at Caltech, Harvard's Department of Earth and Planetary Sciences, ESA's Space Operations Center in Darmstadt, and the European Space Network's deep monitoring stations in Spain and Australia. By sunrise, every major geomagnetic authority on the planet was looking at the same impossible graph. To understand why this matters, we need to step back, just briefly, and remember what Earth's magnetic field really is. It is not a static shell. It is a living, dynamic system generated by the geodynamo, the chaotic, electrically conductive motion of molten iron and nickel more than 2,800 kilometers beneath our feet. This invisible engine shields our atmosphere from solar wind, guides navigation systems, and has quietly protected life on Earth for billions of years. We model it carefully. We update those models every 5 years. We know it wanders. We know it weakens and strengthens. We even know that on geological timescales, it flips. But what happened next does not fit the historical record. 48 hours before today's alert, researchers reviewing preliminary swarm data noticed an unusual gradient forming beneath Siberia. The magnetic flux there was weakening faster than expected, dropping by nearly 30 nanoteslas in just 12 hours. For context, global secular variation usually measures in single-digit nanoteslas per year. At the time, it was flagged as noise. 11 hours later, magnetotelluric stations in northern Greenland detected a synchronized anomaly, oscillations in the ultra-low frequency band between 0.01 and 0.1 Hz, suggesting deep core electromagnetic disturbances rather than surface effects like solar storms. Space weather monitors quickly ruled out solar flares. The sun was quiet. Solar wind speed hovered at a calm 340 kilometers per second. The disturbance was coming from below. 6 hours before the main alert, a team running high-resolution simulations at Caltech noticed that their core flow inversion models no longer converged. The equations broke symmetry. No natural turbulence pattern could reproduce the observed acceleration without introducing a new force or boundary condition. Then, at 2:18 a.m. UTC, the pole jumped. Not physically, of course, but mathematically. Its calculated position shifted nearly 55 kilometers towards Siberia in a single update cycle. That is movement normally expected over several years, compressed into hours. I remember staring at the data feed, refreshing it again and again, convinced there was a calibration error. There wasn't. Within the next hour, aviation authorities quietly issued internal advisories. Satellite operators began checking attitude control systems. GPS correction algorithms were adjusted on the fly. Publicly, nothing was said, but behind closed doors, conversations turned serious. By mid-morning, an emergency virtual symposium was convened. Participants included geomagnetists, fluid dynamicists, computational physicists, and space weather experts. Dr. Elena Markov, a fictional but representative senior researcher at ESA, summarized the mood bluntly. We are observing a rate of change that does not appear anywhere in the modern instrumental record. The investigation moved fast. Spectral analysis of magnetic field harmonics revealed something unsettling. Higher-order components, normally chaotic, were aligning. Not perfectly, but enough to suggest coherence. In other words, parts of Earth's magnetic field were changing in a coordinated way. No natural process should do that on this timescale. Teams ran gravitational coupling models to see if tidal forces from the Moon or even distant planetary alignments could be responsible. The results were clear. The energy required exceeded known inputs by several orders of magnitude. Another hypothesis emerged: a sudden change in heat flux at the core mantle boundary. Perhaps a massive thermal plume had reorganized core flow. But even the most extreme plume models could not explain the speed. That's when the debate began to fracture. The mainstream explanation, supported by most geophysicists, argues that we are witnessing a rare but natural reorganization of core dynamics, an extreme case of secular variation amplified by long-term weakening of the magnetic field. After all, Earth's field has been declining at about 5% per century. Maybe this is simply what instability looks like up close. But others were not convinced. Dr. Samuel Reyes, a computational physicist at a fictionalized Harvard lab, presented a troubling alternative. His team's simulations showed that the observed acceleration matched what would happen if an external electromagnetic influence interacted resonantly with the geodynamo. Not a solar event, not a lightning-induced current, something else. At first, the room was silent. Then the objections came fast. There is no known external source capable of coupling energy into Earth's core at that depth. The mantle alone should block it. The physics forbids it. And yet, the data kept arriving. 24 hours after the initial alert, a second wave of anomalies appeared. Low Earth orbit satellites reported sporadic attitude drift coinciding with localized magnetic fluctuations. Over the South Atlantic anomaly, a region where Earth's magnetic field is already weak, radiation levels spiked unexpectedly, forcing several satellites into safe mode. On the ground, high-frequency radio operators in Scandinavia reported brief blackouts. In northern Canada, auroral activity intensified far south of its usual range, painting the night sky with curtains of green and violet at latitudes that should not see them. This was no longer an abstract model problem. Internal communications leaked, short encrypted messages between agencies acknowledging that the pole's velocity had doubled again, now moving at nearly 80 kilometers per year if extrapolated linearly. Extrapolation is dangerous, of course, but so is ignoring a trend. Then came the pattern. When analysts plotted the acceleration against time, they noticed a rhythm, pulses approximately 96 minutes. That number immediately caught attention. 96 minutes is close to the orbital period of many low-Earth satellites, but also to certain magnetohydrodynamic wave modes predicted in theoretical models, never before observed. The pulses were precise, controlled. This was no longer random, one internal report stated. It was responding. Responding to what? Governments reacted quietly. No public announcements, no press conferences. Instead, task forces formed. Data sharing agreements were accelerated. Defense departments began reviewing contingency plans for navigation outages and power grid vulnerabilities. On Earth, subtle effects accumulated. Migratory birds deviated from expected routes. Autonomous underwater vehicles reported compass errors. Even some long-range ballistic missile early warning radars required recalibration, not because they failed, but because the reference frame beneath them was shifting. In the midst of this, I found myself thinking about history, about how ancient navigators once trusted a lodestone and the stars, about how we built an entire technological civilization on the assumption that the ground beneath our feet is magnetically reliable. And now, that assumption is trembling. 48 hours into the crisis, a new dataset arrived from an unexpected source, deep-sea magnetometers anchored along the mid-Atlantic ridge. These instruments, designed to study plate tectonics, detected minute but widespread changes in magnetic inclination synchronized across thousands of kilometers. This ruled out local crustal effects. The source was global. Two camps hardened. One insisted that we are witnessing the early stages of a geomagnetic excursion, a temporary but dramatic shift that does not result in a full reversal. These have happened before, they argued, leaving traces in volcanic rocks and sediment layers. Humanity simply has the misfortune of witnessing one in real time. The other camp remained uneasy. Excursions, yes, but never this fast, never this coordinated. What troubled me most wasn't the movement itself, but the timing. The acceleration appeared to begin shortly after a series of deep Earth seismic events recorded near the core mantle boundary. Events too subtle to be felt at the surface, but energetic enough to be noticed by global seismograph networks. Coincidence is a word scientists use carefully. As night fell again over the northern hemisphere, the magnetic pole continued its silent sprint. No alarms sounded for the public. Life went on. But somewhere deep within Earth, something fundamental was changing. Maybe we are witnessing a natural heartbeat of our planet, one that simply operates on timescales longer than human memory. Or maybe, just maybe, we are confronting the limits of our understanding, forced to admit that even Earth can surprise us. There's a strange humility in that thought. We spend so much time looking outward, scanning the skies for anomalies, for signs of intelligence or danger. And yet here, beneath our own feet, an ancient force reminds us that the unknown is not always cosmic. Sometimes it is planetary. As I speak, models are being updated again. Emergency revisions to the world magnetic model are underway, something that has only happened once before in modern history. Scientists are watching, governments are waiting, and the pole is still moving. What happens if it accelerates further? What happens if this is not the peak, but the beginning? Subscribe to follow the next update. This story isn't over.